recording this computer, share my screen. I will try to make sure that I get this uploaded as soon as possible. As soon as we're done. Let's see. 1 second, stop sharing. Just making sure I've got everything I need. I want to make sure I didn't have my exam accidentally open. I mean, you would have loved that, I'm sure, but. All right. So I sent out the email. I should be able to I'm fine enough to go through this entire exam. So I'm going to start doing so. That's what I'm going to do today. I'm going to go over this exam. All right. For each of the following questions, indicate which data structure would be best suited to handle each scenario. Your choices are array list, linked list, stack queue, tree, priority queue, set, and map. You will have a series of questions like this just like this on exam 2, as well as on the final exam, where the only difference is that on the canvas, on your electronic version, it's going to look like this. It says it's going to look like this, but with a multiple choice instead. All right, so you need to model. Which patient should be seen next at a hospital. Patients should be seen in as close to the order of arrival, but patients with a more severe situation should be seen first. What data structure is this? Priority, yep, priority queue. Priority queue is correct. So this is a priority queue. Okay. A router needs to hold packets in a buffer and deal with them in the appropriate or with the order they appear. Yep, that's a queue. And remember, to pronounce queue, you say the first letter and ignore all the rest of them. You need to model a hierarchy. Yep, trees are hierarchical data structures. And you need a data structure to hold your previous decision in case you need to backtrack. Yep, a stack. Do not tell me recursion. Recursion is not a data structure. I get that I've gotten that a number of times. So yeah, stack, because basically anything that can be done with recursion can be done with a stack. There might be some weird mathematical exceptions, but if they are, they're extremely weird and you do not have to worry about them. Like I said, sorry about that. I'm sick. So we're going to have a couple of vocabulary questions. I trimmed them for a couple on the exam just to make sure that there's room. And I'll go over what's on the group exam and what's on the paper on the solo exam, what's common and what's not common between them. Okay. The node at the top of the tree is called what?
Root.
Yep, root. The predecessor, the links from a node to a successor are called what? Yep, you could say they're called links. They are links.
Can you say edge?
Branches or edges. Then predecessor of a node in a tree is called what? And let's go with the immediate predecessor. Yep, your parent. And if you're talking about a more generalized predecessor, the term is ancestor. On an exam, the thing is that I will take basically anything that makes sense. A lot of these questions for vocabulary are going to be fill in the blank. Nodes that have the same parent are what? Siblings, yes. Describe without using code how to calculate the height of a tree recursively. So first off, let's describe what the height is. The height of a tree is the number of number of levels it has, right? So here we have 3 levels, so it's got a height 3. It is the length of the longest path from the root to a leaf. The longest path from a root to a leaf is its height. With the path length being described in nodes in this class. Now, how do you calculate the height of the tree recursively? It's very simple. The height of a tree is equal to is equal to 1 plus whichever one is bigger. Right? It's equal to 1 plus the height of a tree is equal to 1 plus whichever one is bigger of the left versus whichever one is bigger on the right. Sorry. Yeah. The height of the tree is 1 because the tree already, if you've got a node, you know it's going to be at least height 1 plus the height of the left or the height of the right, whatever is bigger. You can do that with an if-else statement in code or a math.max. All right, so draw on an example of each of the following binary trees. Use a different example for each tree because if we didn't, I could just say this and say done because it's both full, complete, and perfect. So we're going to go with different examples. So a full tree, all nodes have either 0 children or 2 children. So this is a full tree. That's not a full tree. This is a full tree. This is a full tree. This is a full tree. That's not a full tree because because this does not have a child there, right? So that is not a full tree. Make sense? But this would be a full tree. Make sense to everybody? Everybody understand what a full tree looks like? 0 kids or no kids. Everybody. It's like the opposite of Highlander. There cannot just be one. Okay. All right. So perfect nodes. So perfect trees follow this equation. A perfect tree is a tree of height h that has 2 to the h minus 1 nodes in it. Now, what that means is that there's literally only one way to draw this. A height 1 has 2 to the 1 minus 1 node in it. If it's height 2, that's 3 nodes, and there's only one way to draw a tree with 3 nodes. That is basically that it's balanced, I should say. And 2 to the 3, that's minus 1 equals 7. So only one way to really draw this balanced out. Ta-da. Make sense? Basically, anytime we see like a kind of mathematically, aesthetically symmetrical tree, it's perfect. The next level would be this. And this is working for everybody. Everybody's able to see my horrible chicken scratches. Okay, great. All right, next one. Complete tree are probably the most annoying. So complete trees are perfect up until the bottom layer. So it's perfect up until here. And then we fill them in left to right. Perfect trees are used for heaps. Heaps are always perfect. Complete trees are always used for heaps. Anytime that we need an array-based kind of notation, this is where it works because you would go, this is index 0, index 1, index 2, index 3, index 4, index 5, index 6. So when there's an array in the back end, we really like having these complete trees because it means there's no gaps in the array. So for a complete tree, this layer has to be filled from the left to the right. So this is a complete tree. This is still a complete tree. This is still a complete tree. This is not a complete tree because there's a lot of gaps right here. Make sense? Similarly, if we don't have a node here, but we have one here, also not a complete tree. This is a complete tree. This is still complete. Not complete because we have two missing. We've got this gap over here. Make sense? Complete, 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 not complete. Tree operations. Expected question. So you'll get this question in a couple different ways. Actually, you'll get this question. So you'll get the add and remove drawing questions on the paper exam and on the solo portion and the group portion. I'm not going to, I think for the group portion, I just have removal because time considerations. But on that exam, you'll draw it. Here, you'll in the on the solo portion, you're going to do it, by multiple choice. So my one thing I would say to everybody is that if you have scratch paper or work, please turn it into your TA. That way I can give you partial credit in case you make a mistake in the middle. Okay. Because, multiple choice is typically a bit cruel if you're, if in situations like that. So let's see. So draw a binary search tree that forms after inserting the following integers. So what we're going to do is that 42 is the first node, so it becomes the root. 10 is less than 42. 50 is greater than 42. 12 is less than 42, greater than 12, so it goes here. 17 is less than 42, greater than 10, greater than 12, so it goes here. 80 is greater than everything, so it goes all the way to the right. Negative 12 is less than everything, so it goes all the way to the left. 100 is greater than everything, so it goes all the way over here. And now 96 is greater than 42, greater than 50, greater than 80. But it's less than 90, but it's less than 100, so it goes over here. 105 is greater than everything, so it goes over here. And then 86 is greater than 80. Less than 100, less than 96. And 72, which is less than. That looked right to everybody? Okay. Double checking. I always like to double check these things. 42, 10, 50, 12, 17, 80. Negative 12, 100. 105. Okay, nope, not 105. 96. 96. 105. 86. 72. Okay. Now, using your previous answer, because I'm lazy, draw what happens when we remove the following. All right. So there's three cases for removal. If we remove something, if we're trying to remove a number that has no children, like 86 down here, that's no problem. We just kind of just delete it. If we have one child, like in the case of we're removing 96, what we would do is that we would just connect 86 and 100. That's all we have to do. But if you have two children, you have to basically replace and remove. So what I mean by that is that you have to basically find a node that satisfies the property of keeping the entire tree in order. So the only thing that so for instance, here we're removing 42. That means that we have to find a node that if we place it at the value, if we place it at the root, all the numbers to the left of it will be less than it. All the numbers to the right of it will be greater than it. So there's only two options, which is the next in order predecessor and the next in order successor, which means, in other words, the biggest thing that's smaller than me or the smallest thing that is bigger than me. I like to do the next in order predecessor, the smallest thing that is bigger than me. So that means to find that, I go all the way to the left. Sorry, one step to the left, all the way to the right. In other words, I look at this subtree over here, and I find the biggest thing in this subtree, which is the node all the way to the right in that subtree. And it's got to be the thing all the way to the right. Because if there was another node to the right, it'd be bigger. And if there's something to the left, it's smaller. It's that simple. Okay. So we take 17, and what we do is that we will put 17 over here, and then we'll delete the so what we'll do is that we'll take 17, make it the new root, and then delete 17 from this subtree over here. This works best. That works best if you're going to do it with assuming there's no repeats here. Okay, now removing 12, that's the case of just removing something with no children. Boom. Removing 17. We need to find the biggest thing in this subtree. So we go 1 to the left and all the way to the right, which gets us to 10, ironically, because 10 has nothing to the right of it. So we say, okay, place 10, then remove 10 from this subtree. To do that, 10 needs to be adopted by 10's child needs to be adopted by its parent. So we remove this and connect over here. And then now 96, same deal over here. All right, I'll keep going. Which of the following is a pre-order traversal for a binary tree? So first off, for these two questions, which are pre-order, post-order, blah, blah, blah. The left, no matter whether it's a pre-order, in order, post-order, the right never goes before the left. So D is just straight up wrong. Make sense? Okay. So otherwise, the only difference is that where is the root node in all this? And the root node is either processed first, processed in between, or processed last. For pre-order, it's done because the root node is processed first. So pre-order, in this case, would be B. And post-order, the root is processed last. So C. Heaps. Draw the minimum heap. So min heap, we always add the small, so with a heap, the heaviest things sink to the bottom, where the largest values rise to the top. Okay. And the important thing to remember is that as these heaviest values sink to the bottom, as we're adding these values, we are adding them such that this heap would form a complete tree. So 8. So the next place to add something is 10. 10 is heavier, so it stays on the bottom. 50. So we add it here, right? So we don't do 8, 10 because that's a tree, not a heap. All we care about with heaps is the root of the heap the lightest item, the smallest item. 20. Now we add 1 over here. 1. And so each time we add a node, we check it against its parent. Each time I've added it, every node has been heavier than its parent. But here, 1 is lighter than 10. So they swap. Similarly, 1 is lighter than 8. So they'll swap. 1 is at the top, so we can't do any more swaps. All right. So also, after adding this, notice that the root of the heap is the smallest item, but also each sub heap, like over here, has the smallest item of the sub heap as its root. Let's go ahead and add 4. 4 gets added over here. It needs to swap with 50. But it doesn't bubble all the way up because it's heavier than 1. Then we add 3 and we swap with the 4. So that is our remaining. So that is our last heap. So using the heap you drew above, draw the heap after removing an element twice. So to remove an item from, why are there bigger items on the left? Because this is a heap. We do not, left and right doesn't mean this, it don't matter. Left and right values don't matter anymore. No, we don't, there's not gonna be any array, adding or removing items from the array or the heap. We don't really need to concern ourselves with the underlying array based array thing. I have only so many topics I can touch on. And so that is not a topic I'm gonna touch on. So remember, all heaps care about is, does the smallest, when we add, is, are we adding things in a way such that it remains a complete tree? And are we adding things so that the smallest item is going to be at the top? So now to remove it, we need to when we remove something from a heap, we remove the top item. But of course, that means in order for it to remain a complete tree, we have to put an item there instead. So we remove the only item we can to maintain it. So we take the only item we can and move it so that it maintains the complete tree, which is 4. So we take the last item, the item from the last position, and move it and use that as the root. So 4. And now, though, the heap is all messed up because 4 is not the smallest item. So what we do is that we take 4, we look at both of 4's children and say, hey, is 4 heavier than 8? If it is, it should sink. Well, it's not, so it doesn't sink. Is 4 heavier than 3? Yes, it is, so it should sink. And now we ask, is 4 heavier than 50? It's not, so it stays put. Now, if we do a second remove operation, that means removing the 3 and replacing it with 50, because 50 is the next value we can remove because it's at the back of the heap. Okay, now 50 has to do some swapping. Is 50 less than 8? Yes, it is, but it's also less than 4, and we need it to swap with the smaller so that the smaller item bubbles to the top. And that's what we get after removing it twice. All right, Huffman coding. I don't think I've done the Huffman coding problem in like 2 years, so this is gonna be fun. All right, for Huffman coding, we've got basically some imaginary document that's made up of A, P, L, E's, and 1X. Okay. A occur, and so what we need to do is that we want to order these symbols in the order that by frequency, how often they appear from smallest to greatest. So X appears once. And the reason we want to order them from lowest to greatest is that the lowest item should be closer to the bottom of the tree because they're going to be rare. So X appears once, L appears 20 times, P appears 40 times, A 50, E 60. Nice, great. Okay, so we've taken this and we've set up our queue, but it's not just any queue, it's a priority queue, and that's where most of the mistakes in this problem come from. A priority queue means that as we add things to this queue, things are going to need that the queue is going to resort itself. Because a priority queue uses that heap that we just did above as an underlying array. Now, the Huffman coding problem is going to be on the paper version of the exam. So in other words, only on a group. So you're only going to tackle this problem as a group. For the past couple of years, I've left the Huffman coding off the exam, but that's because like we had a lot of COVID situation. Now I'm comfortable putting it back in. And as such, I want it to be a group exercise here. That's hard to say. There's two programming questions on the individual exam. One feeds into the other. I'll get into that. But also like some of the I mean, like there's like 10 or 12, but some of them are short questions. Like the aforementioned, choose the best data structure. So less heavy hitting questions. Yeah, same rules that apply for this exam. It's open note, open book, open whatever, with the restriction that you can't Google stuff. It's the same rules on top of the exam as the last one. So, okay, let's go ahead and do this. So now to start creating our Huffman tree, what we do is that we dequeue twice. We get the first two symbols from this tree. So we say X and L have a combined weight. I need to put these on the bottom, or rather I need to put this over here. X and L have a combined weight of 21, right? Because X and L, if we consider them as one thing, they'll appear 21 times in the document. So what we're going to do is that we're going to take this 21 XL and add it back into the queue. But because it's a priority queue, the smallest number has the highest priority. So it's going to go to the front of the queue. Next, we dequeue again. We just dequeue dequeue the XL node and the P node. The thing we dequeue first always goes on the left, and the second thing goes on the right. P had a weight of 40, 40 plus 21. This means these together have a combined weight of 61. Now we add this in, XLP. Okay, go ahead and move my face stuff over here, out of the way. So now this has a combined weight of 61. Next, we have A and E. A and E, we add them together. They have a combined weight of 100. So we dequeue those. It is a combined weight of 110. And we add this node A and E back in. And finally, we have two nodes to dequeue, 61 and 110. We add them together into a single node that has a combined weight of 171. This should be what you're getting, right? Everybody else get this answer? I normally am more confident, but again, I'm working through sickness. Sort of. All right. So now, so these two questions, by the way, are, I should mention that while we have 2 questions here, the way I grade them are disjointed. In other words, you draw a Huffman's tree, you get you get full credit, no credit, partial credit, whatever. Well, not whatever. I mean, it matters to you, but you do this and it's either correct or not correct. Regardless of that, if you use that Huffman tree for problem 15, the encoding part, I'm going to assume that you got it right in 14. In other words, this part is correct based on what you put in over here, not based on what my answer. So even if you missed the first part, you can still get the second full credit on the second part. So encode the string apple into binary using this encoding. So we use 0. So we put zeros on the left branches, ones on the right branches. So to encode apple, we do 1 0 for A. So 1 0 for A. For P, we need to get to P, so that's a 0 1. Another P, 0 1. L is 0 0 1. And then E is 1 1. So that is our binary string. Sorry, again, I am still a bit sick. Thought I would be a bit better today. I am not. All right. So again, that will be on the group portion. So please study for that. That is the important part. So, okay. Let's see. We've got ourselves a new project exam to F2020 to practice. You always get shocked when I find out what year it is. Doesn't matter what year it is. Ever since 2020, it's just kind of been all one long. Time has had no meaning since COVID started in spring 2020. All right, so here, what we need. So all we need to basically make sure that this compiles is, and all I'm going to bother putting down. I mean, you can use my full tree code, but I'm not going to bother. I'm just going to create for coding purposes, I'm just going to create move all this stuff over now to the other side. Because I'm sure you're seeing like a static kind of thing overlay on it. Okay. So private static node. So private static class node E E second. There we go. E item. Node E left. Node E right. And while I can't really test my code using this, I can definitely write my code. Public node E item. Sometimes I call it item, sometimes I call it data. Don't really care. Okay, there we go. We've got ourselves a node class. Great. So now what I've got here is size tree. It does it as a static method. Honestly, it doesn't matter. Here we're passing in a node that is the root, and we're asking to figure out what is the size of the tree. And also with the caveat, please forget that the size method exists, right? I want you to calculate this, by literally counting each node one by one. Go ahead and just return a value. Okay, right. It's not Python. I can't just randomly hit. I have to have some limit. Okay, to figure out what the size of the tree is, let's figure out our base case. My base case, one base case is that, right? Basically, there's a couple situations of what this root is going to be. Root is either going to have, which can be classified into two things. One, I get past the null. The other situation is I get past a node, and that node has a left subtree and a right subtree. Now, those left subtree and right subtrees, those could be null, right? Those could be null, but this guy isn't, and that's all I care about. Okay? So if I'm past a null value, so if root equals null, so if, it doesn't exist, then the size of the tree is 0. Make sense to everybody? Otherwise, we're being passed this situation right here on some node with a left subtree and a right subtree. Now, we know that because we have a node and it's not null, that it's got to be at least that we have at least one node. So we have at least one. But the total size of this tree or subtree is equal to 1 plus however many are in here plus however many are in here. So I'll say the int size is equal to 1 for me. Size is equal to size plus the size of my left subtree and also the size of my right subtree. Make sense to everybody? I mean, yep. Well, I'm glad it makes sense so far because guess what? That's all we have to do. Return the size of the tree, my size plus the left size plus the right size, which we can just simply condense into being return 1 plus the left size plus the right size. That's how big a tree is. Okay. Okay, explain the return one more time. So what we've got here is that a tree, the tree has basically 3 parts, right? We have int my size, which is 1. We have the size of the, we have the left size. So the size of my left tree is going to be equal to whatever. So this is a recursive problem. So the idea here is figuring out the size of my left side is really hard. I don't want to do it. So I'm going to make my left subtree do that. And he'll tell me what it is. Same for my right subtree. That's a really hard thing. So rather than doing it myself, I'm going to be lazy and recursively call my right subtree. He'll figure that out. He'll figure out his own children's size, tell me what it is, and then I can just, add the, and I'll just simply get his right size. Sorry, I'll get my right size from my right child and my left size from my left child. And then all I have to do is just add my number in. That help explain it? My size plus plus. Well, if you did over here, that would only mean we would only ever return 3. I could do my size plus equals, right? But we need to add this value directly in. And like I said, it's just simply, if I'm going to start shortening it up, I'm going to be using it this. I'm going to be making it as short as possible. If I'm going to make it readable, I'm going to make 3 variables. Okay. Is full. Given a tree, returns whether the tree is full tree. So this one is different because from any that you've kind of had as examples, and I like that because of it. But it's still one you can do recursively. So call it root, call it tree, it doesn't really matter. So first off, we've got some base cases here. Okay, first off, the question is this a full tree? Is null a full tree? If I get past in a no, I don't know. I'm gonna go. I honestly, I really don't know. So, but I'm gonna go ahead and say, hey, if the tree is null, then technically every node has 0 children or 2 children. So I'm gonna say return true. Make sense? So that's a base case taken care of. Otherwise, the tree isn't full. Otherwise, we're given a tree. And we've got some more base cases we can take care of, which is that if I have no children, I can just go ahead and check my children. This is what makes it different. I can just check my children and ask them if tree.left is equal to null and tree.right is equal to null. So if the left subtree and the right subtree are both null, then return true. This subtree is a this subtree would be a full tree because it has no children. Every node in this tree or subtree has no children. So return true. Make sense there? Else, if, and I know technically I could just do this with an if because I do a return, but honestly, I like being explicit with my ifs. Nope. These are all base cases. We've got 4 base cases here, actually. Yeah. What if now, if I've got a left subtree, sorry, if I've got a left child, but not a right child, that means I only have 1 child. So I can return false, right? I'm a node. if I'm a subtree and I have only 1 child, congratulations. This is not a full tree. Similarly, if we get into this situation where I have a right subtree, if I have a right subtree, but not a left tree, I again only have 1 child. So these cases are so this is the other base. So these 2 base cases go together if I have only 1 subtree. So if I only have 1 child. Make sense? Yeah, sorry. Just, yeah. The last case is what? The last case is if I have 2 children. Now that's where we get into a problem. So I have 2 children. I know that I myself am full, but the entire tree being full depends on whether or not my kids are also full subtrees. So return. So this is the last statement, and this is where we do our recursion. Return. So let's create 2 Booleans. I'll break it up at first. Boolean left full is equal to is full tree dot left. So I'll figure out if my left tree is full. Recursively. And I'll do the same for my right. And if they're both full, then the entire tree is full. Both halves of my tree are full. Well, I also have 2 children, so I know the entire thing is full. And of course, we can just simply break this up by simply doing this over here and putting this in there. Any questions on this one? So again, these recursion, these state, if you know how to do your recursion and you've come, once you figured out how to do recursion, these statements are very short and to the point. I'm going to go ahead and do this one. This one is definitely harder than one I would put on the exam.
Professor?
Yes.
How would the last example handle if
Sorry?
a node has 2 children?
Sorry?
How does this handle a node having 2 children?
How does it know that it has 2 children?
Yeah.
Because of the if-else branches. We know that the node has to have 2 children because it exists. It doesn't have 0 children and it doesn't have 1 children. Make sense?
Yes. But at what point would it return true?
Sorry?
For that?
Well, we don't return true because if I have
true for that?
We don't return true because because all I'm able to do right here with recursion is I can make a local decision. I know I have a existent left tree and right tree, but I don't know what they have.
Okay. Yeah.
As children. So I'm asking them to figure out, okay, because if this side is not full, then the entire thing is not full.
Yeah. Okay, I understand.
Mm-hmm. Okay. So the equals problem. Write a method which, given 2 trees or subtrees, returns whether or not the contents of the entire tree are identical. In other words, they store the exact same data in the exact same way. So in other words, I'm going to say that like if I've got 2, so if I've got 1, 2, 3 stored in a tree, right? These 2 trees are equal, right? Because they have 1, 2, 3, and 1, 2, 3 is presented in the exact same way. On the other hand, these 2 trees are not the same because while they have the same data, they don't have the same structure. Make sense?
Yeah.
So that's what I'm doing for the purposes of this problem. If you only cared about the data, it's fairly straightforward. You just do an in-order traversal and see if the in-order traversal is equal to the is equal. That will work for most cases, but public. Here we go. Okay, we've got ourselves a left subtree and a right subtree. We got to do our e's over here. Let's go ahead and make some blank spaces so I can put this at the top. All right. Sorry. Will I post this somewhere? I mean, I'll upload this online and I'll try to remember to put this on Discord. Okay, so let's do this. So, how can I tell? So we've got 4 options essentially here, about what we're getting passed in for node A and node B, and it all depend. Oh, sorry, for tree A and tree B. Okay. So option 1, they're both null. Option 2, one is null, but the other exists. We also have the other exists. So, you know, the right exists or the left exists, but the other one does not. So those are options 2 and 3. And option 4 of what we get passed into this function is that we get 2 trees passed in. So if else statements, if tree A equals null and tree B equals null, then null is null, so they're equal, so return true. Else if, and I will just copy this bit over here. Else if A exists, but B doesn't, return false. Something and nothing are not equal to each other. Same over here. Something and nothing are not equal to each other. Make sense? Else both of them do exist. Okay. First thing to do is we want to check if tree A dot item dot equals tree B dot item. So check if their values are the same. If they are, great. Otherwise, return false. If they aren't equal, then the trees aren't equal because they have different contents. But if tree A and tree B are equal to each other, or the items in them are equal to each other, then what we need to do is pretty much what we did for the is full. What we're going to do is that we check node, not node. We say, hey, tree A dot left and tree B dot left. Are you equal? We're going to check if our left, so if we know that we are equal, like we have the same contents, then I'm going to ask, then we're each going to ask our left trees if they're equal. And we'll also ask the same question to the right trees. Tree B. This is surprisingly difficult for me for some reason. There we go. So there we go. Recursion.
Sorry.
Yes.
What would tree A dot item return?
Tree A dot item. It's just the item that's stored in the node. In other words, it's the contents of the tree. So if, again, if our trees were 2 and 3, tree A dot item would be 2, tree B dot item would be 3. So this check would be false. So the trees would not be equal. On the other hand, if we did 2, if it was like this, we would see 2 is tree A dot left 2, tree B dot left 2. So tree A dot left. Sorry. We'd see that tree A would have 2, tree B would be 2, true. And then we check the lefts against each other and the rights against each other. Okay. I'm not going to bother with question 20. There's nothing like it on the exam. Hash map. That's a coding question that's been moved to the group portion of the exam. It's not, and if you've been paying, again, if you've been paying attention to your lectures, you know exactly what question you're going to be getting. Or you can probably or rather you should be able to make a very excellent guess as to what kind of question you're going to be getting. So here we've got what we want to do is, given a string, count how often each character occurs. So what I'm going to do over here is I'm going to simply copy this over, say map is equal to new hash map, boom, return map. And now we just need a for loop to iterate over the string. Easiest way is to do, so the way you probably know off the top of your head is to do something like this, word dot length with parentheses, because Java's silly like that. And then we would say car C is equal to word dot car at. It's perfectly fine to do it this way. I don't like doing it this way. It's a perfectly fine way to do this. When a programming language provides me with a for each loop, I like using a for each loop. For car C for every character in Word. However, Java doesn't like me using a for each loop on a string for some reason. It's ridiculous. I don't know why. So what you have to do is I have to convert this into an array of characters, and now it works. Because strings are just arrays of characters. So for every character in the word, if map dot contains key C. So if we've not seen the character before, congratulations, I've seen it once. Map dot put is equal to C1. If I haven't seen it before, sorry. So that's if I haven't seen it before. If I have seen it before, get the amount of times I've seen it, and then update the map accordingly. And that's it. Okay, I'm just going to quickly move to the other problem so that the analysis problems, so that I can go and then, give you an overview of what to expect on the exam itself. Oops, sorry. Just share. Sorry, I'm also kind of running out of energy here, so giving it my best effort here. So what are collisions in the hash table? Why do they occur, and how are they handled? Collisions are when two keys try to occupy the same index in the underlying array of a hash table. This occurs because the universe of keys is bigger than the underlying array. You cannot make an array of infinite length, but there are an infinite number of keys potentially. So we try to make our hash table big enough to accommodate the size of this, but occasionally we get collisions because the hashing process is never really truly going to prevent all collisions for all possible instances. Okay. So that's why they occur. More importantly, how are they handled? They are handled by they are primarily handled in computer science text by one of two ways. The first is called open addressing. So here I'm getting my pen. Okay, so the two ways to handle it are open addressing, which basically means let's look for the next, which basically says if my spot is taken, I'm going to look for the next available spot. There's two ways to do this that we've seen. There's open addressing with linear probing, which means I need to look for the next available spot. I'm going to look for it literally by looking one over. So if this spot is full, this spot is full, this spot is full, and I'm trying to go here, then I'll look, and end up here. The other way is quadratic probing. Which means that instead of if I can't have my spot, I'll look one away, then I'll look two squared away, then I'll look 3 squared away, then 4 squared spaces away from my original spot. Now, the reason you do this is linear probing creates clumps. Quadratic probing is better at creating these clumps where you can have a lot of collisions, but the process of doing a multiplication operation is slightly more expensive than just simply doing an adding operation with linear probing. So it's kind of a small trade-off. The other way to do it, which is very popular because of how simple it is bucket hashing or chaining. And that's basically saying, oh, well, instead of having a slot, each of these is instead the head of a linked list. And so if I add my node, so if I want to add something to a link to this, then I just get to my slot and add and append it to the end of the linked list. And what you do is that if you've got a good hashing function and you basically rehash once the average length gets above some constant, you can maintain a constant runtime. Yes, it's hacks. It seems like it's cheating, but it does work. So what is the worst case runtime for the insertion and deletion algorithms in a binary search tree, and why? The average case runtime that we typically talk about is log n, specifically log base 2 of n. But that's if they're not self-balancing. If they're self-balancing, the worst case is log n as well. But the kind of trees and the tree algorithms we've been working with, the worst case runtime is O of n. And the reason for this is because that the log of n runtime assumes a balanced tree that each side roughly has the same amount of nodes. Something like this. That's technically balanced, believe it or not. But if we don't have any kind of rebalancing algorithm, then there's nothing stopping us for creating a tree that's linked list with extra steps like that. Or let's just take a look at this sentence or these letters. Actually, even easier. Actually, these words. The quick brown fox. You've all seen this sentence. Jumps. You've all seen this sentence, so I'm not going to bore you. So the gets inserted first. Quick, QRST, Q comes before T. The quick brown, all the way to the left because it comes alphabetically before. Fox comes before comes before this, comes after brown. Fox jumps over lazy. And you get the idea. What's going on here is that each step we aren't what's going and so the reason this is O of n is because with a log n runtime, what you do is that each step you take cuts your search space in half. Here, each step we take cuts our search space by 1. All right. So now I'm going to go and pull up my exam so that I can the exams on my end so I can actually look at them and tell you accurate information. Okay. That's why I'm not sharing my screen anymore, because if I was, you'd be able to see that, and that kind of defeats the point of giving you an exam where you don't know what the questions are. And I'm sick, so I would very much not like not to have to rush to like redo all these questions. All right, so the total, so the exam is 14. And again, sorry, I'm just kind of feeling really sick. So there are 14 questions on the exam. Questions 1 through 4. They are your multiple choice questions that I've told you about. The ones that are on the practice exam that are not multiple choice, but are the first questions on the practice exam. Given a data structure, tell me the best one. So those don't take too long, maybe a minute, maybe a minute each. Then I've got question 5, question 6, and question 7 are fill in the blank vocabulary questions, just like you did on the second page. Question 8 is a question about adding. Basically, a question about like, okay, what trees form after adding stuff. Question 9 is about traversal. 10 is about deletion, right? These are all questions that were on the practice exam, right? Question 11 is our heap question. Questions 12 and 13 are coding on trees. Question 14 is our analysis question. That's your solo exam. Everybody got it so far? Good. Group exam. Will look longer than it is. It's 4 pages front and back, but the first page is just scoring and some extra notes. 14 was our analysis, 11 was heaps. Your group exam will have, let's see. So your group exam, as I meant, will have some stuff that was not on the, so for instance, like if your group exam will have like an add or remove question on it, okay? But the add or remove question on it will be like, it will have, well, let me check. Yeah, it will have, it should have, it's going to be done on paper. You're actually going to have to draw and show me your steps. Question, then you've got the question on Huffman encoding. I'm going to re-ask the same questions. So the same tree programming questions that were on the exam, you're going to have those on the group exam as well. And then the hash table, the map question will be on the group exam as well as the analysis question. So overall, there's going to be 3 new questions on the coding front. Sorry, 3 new questions on the group front, not the coding. Okay. And again, remember, the group portion cannot hurt your grade. It can only help it.
Could you show your GitHub?
My
Where the
GitHub?
code is here? Yeah.
Give me 1 second. Something about the runtimes of either hash tables or of or trees. Okay. Give me 1 second. Close this. Just again, making sure that I don't have. I have to be extra cautious since I'm, tired. Again, sickness is not fun. So the GitHub, my GitHub repository, which you can use during the exam, you're more than welcome to. You go to your Canvas page, go to the other important links right over here, bottom link over here. Make sense?
Yeah, I'm just asking like where what is stored,
Sorry, where would what?
where each topic is stored. Like
Oh.
these heaps.
So if you go into the destruct folder over here, it's in folders.
Okay, thank you.
I'm not sure where. Let's see. Where did I put trees? There should be trees here, I would think. They're not trees. Ash.
It's in spring 2018.
Oh, geez. Okay. Apparently I didn't redo trees there. Okay. Yeah. You're allowed to use if it's so again, the rules for exams. It's the same rule as I used over here. Same rules, 70 minutes on the solo portion. Oh, come on. Did I not send out the instructions for? Oh, here it is. So here's the rules. You can use your own computer or the lab computer. You can use any IDE. It's open note. Note can be on paper or on the computer, or it can be the textbook. You can use whatever paper you bring in. Notes can also be code stored on your personal cloud. You can use any resource on the internet so long as that resource can be accessed from my Canvas page. So you're allowed to use YouTube. You're allowed to use, my YouTube links here. You're allowed to use GitHub. I suppose the one exclusion is using Discord to talk because, communicating with other people during the exam. But basically you can use my GitHub and my YouTube, as well as anything on here, including the files.
How about code stored on Discord?
You want to download it if it's not on Discord. I mean, the thing about Discord is, that's fine. As long as you're not as long as you're not communicating on Discord, I would prefer you not have it, and download it in advance. Let me go ahead and drop what I wrote in Discord to begin with so that, I don't forget to do it later. But otherwise, that is it. I wish you the best of luck on the exam. Students, if they study, generally do much better on this exam than the second exam, than the first exam.
Thank you, Dr. Rosen.
Okay. So stop sharing.